So our next discussion on unsteady performance is going to be focused on takeoff and landing. Now, in general, takeoff and landing both consist of multiple phases. It's not just the portion of the ground roll where the wheels are in contact with the runway. We also have to consider the transition as the aircraft starts to rotate from its normal horizontal position on the runway as it's accelerating to takeoff velocity to its climb out scenario. So there'll be a transition period as it rotates, increasing its angle of attack until it gets to that climb out attitude. Then we also have to include a brief distance, horizontal distance, for the aircraft to actually gain some altitude. And typically this will be around 50 or 35 feet requirement, depending upon the particular aircraft, whether you're, for example, a heavy aircraft, a light propeller-driven aircraft, or military aircraft. So you have to look at all these different phases. In addition to the landing phase, you'll also include an approach phase as well as that transition free roll phase before the pilot begins to apply the brakes, and then finally braking distance. That includes not only the impact of braking wheels with brakes actively engaged, but also perhaps a thrust reverser. Now, why do we include this 35 or 50-foot screening altitude? If you look at many different runway configurations across the world, what you'll often find, particularly in urban settings, is that you'll have some obstacles perhaps near the end of the runway. There tend to be limitations on things such as height of buildings and trees, but based upon when the runway was constructed and where it's located at in the urban landscape, there is a possibility that you could easily have a building right off the end of the runway. In this example here, we see the Lindbergh runway in San Diego, which has a building right off the end. And so this is something obviously that the pilots will have to consider when they're going through both the takeoff and landing phase. Midway, as another example, you'll notice the runways are pretty constrained. There's not a lot of distance if you happen to roll over the end of that runway. As well as in many rural settings, you'll often see nature getting in the way, and so the location of your runway may be impacted by surrounding geography. So you'll have to take that into account as well in terms of the performance requirements for your aircraft. Likewise, there's also the possibility of just running into other obstacles on the road, wildlife. So it's not uncommon, particularly in bush aircraft, aircraft operating in Alaska or in Africa, where you might encounter wildlife imparted on your runway. In many of these cases, there aren't fences to keep the animals out. Even if there were, many animals would be able to easily incur upon your runway, austere as it is. We've shown this video before. This kind of gives you an idea about the importance of the height of obstacles and the takeoff and landing procedures that the pilots have to go through as part of their operation. So we'll play this short clip here to illustrate this.
Aircraft manufacturers have tried to fix that problem by designing the pilot out of the cockpit. This is the first fully automated plane, flown by a computer.
So in this particular A320 crash, which was Air France Flight 296, it was a demonstration flight of the new A320 vehicle. 3 people out of the 136 that were on board died in this crash. So the goal was to have a very low flyover height, lower than the surrounding obstacles, primarily for photographic opportunities, so you can get some cool PR pictures out of it. So this was a very slow speed, and it was reduced to reach the maximum possible angle of attack. As part of this, the flight control computer idled the engine so that it was thinking that it was in a landing phase, and by the time that the pilots we're able to apply what's called togo power or toga power, takeoff go around power, so that way you could essentially abort that landing and come back around with a very rapid climb out. The engine's actually spooled up far too late, and you can hear the engine spooling up as it's already impacted into the trees. So as part of this, the FAA, through the FARs, define a number of different aircraft speeds based around the performance requirements and performance parameters of the aircraft. These are only a few of the speeds. If you look up the entire list, you'll see there are literally pages of different speeds that are going to be defined for various points in the aircraft. You can actually take these speeds and map them back to the Venn diagram that we talked about previously, and then denote where each of one of those speeds are located on that Venn diagram. So we're just going to talk about the most relevant ones that pertain to takeoff and landing requirements. Now, all these first are based upon the stall speed, and you'll see, the stall speed is going to depend upon what type of configuration that you're in. We're going to focus on takeoff right now. So we're going to assume that our aircraft is in a takeoff configuration. So for any aircraft, you'll have a flap setting for your takeoff configuration to increase that overall lift coefficient as you're rolling down the runway. Now, from this, we also have a minimum control speed with what we call OEI, or one engine inoperative. This essentially provides us that minimum speed required where we can still control the aircraft. This is particularly important in a twin engine aircraft or multi-engine aircraft, where if we lose an engine, the asymmetric thrust needs to be overcome by our rudder capability on the aircraft, or whatever other yaw control system that we have on board the aircraft. I will talk about this later when we come back and talk about control systems on the aircraft, and this will essentially be our sizing requirement for that control system at this particular point. What you'll notice is there's not a relationship here between the VS and the VMC in general under FAR 25. However, that may be revised based upon where your specific aircraft is operating at, what the environment it's operating under. So then we'll have what's called the decision speed. Again, this is based upon the OEI, and this refers to what's called the balance field length of your runway. We'll come back and define what that is. But essentially at this point, if the pilot is above this velocity, if they lose an engine, they're going to go ahead and continue on throughout the takeoff of that aircraft. If they're below this velocity, then they're going to brake. And this is also going to determine the landing field length requirement. It's not the minimum distance that you have to take off, it's that minimum distance that allows you to safely slow the aircraft down if this particular incident were to happen. And this velocity is required to be above the VMC, so that way you're above this minimum control speed requirement based upon losing that engine and still being able to control the aircraft. Now, all the other velocities then are kind of based in relation to these. We have the rotation speed, which is going to be 5% above that VMC speed, so that way you're at least slightly above that velocity. You have the minimum unstick speed, which is slightly then above your stall velocity. And note, it's just greater than, so there's no requirement on how big that's going to be. Then we have the liftoff speed, which is 10% above that minimum unstick speed, or in the case of an OEI, it's going to be 5% above that minimum unstick speed. And then finally, we have our V2, which is our climb speed to get us to that 35-foot minimum obstacle requirement. And you'll notice that this is defined to be 10% above the stall speed, or 20% above the stall speed, or 10% over that minimum control speed. Now, if we start to look at the basic forces on the takeoff, we can go to our equation of motion that we derived. which is, now that the aircraft is in this horizontal attitude, is overly simplified. So we have our forces acting on the aircraft on the right-hand side, thrust and drag, and then we have the acceleration, basically from our m times acceleration, acting on the left-hand side. What we want to be able to do is solve this equation to determine what the velocity is of the aircraft as it's rolling down the runway, as we have variation in both our thrust and drag forces. Because as we're accelerating and changing our velocity, we know that in most aircraft configurations, our thrust is going to change, but definitely our drag is going to change because our drag is going to be a function of that velocity. Now, there are some additional forces acting on the aircraft. Namely, we have the rolling friction, so that's retarding the motion of our aircraft. So that's going to be the vertical force acting downwards, and so that's going to be a function of both the weight and the lift that we're generating on the aircraft times our rolling friction coefficient. So we'll have to add that into the equation as well. And this then gives us a baseline equation to be able to calculate what that velocity is as a function of these three forces, or so I should say four forces, our thrust, our drag, and then our friction forces, which is a function of both the weight of the aircraft and the lift of the aircraft as it's rolling down the runway. And since these four forces are a function of velocity, they're also going to be a function of time. So in this case then, we can then derive the equation to calculate that time. Now what we're really interested, however, is the distance. So first what we do is we go through the process of rearranging that equation by looking at the overall forces here, F, acting on the aircraft, and then reconfiguring that and integrating that to be able to calculate the velocity and then the time. So at any given point, for any given time in our roll, we'll be able to look at the velocity that occurs at. So rather than calculating this as a function of time, we can calculate it as a function of velocity, because that's what we're really interested in. Where on the runway are we at any given velocity of the aircraft, or what is our velocity of the aircraft at any given location on the runway? So once we do that, then we can then calculate the distance, which is just a function of velocity times time, put that back into our equation, and then integrate it. So that's fairly straightforward. Once we have that solution, then we can put back in the substitution for our forces here that we derived on the right-hand side equation for that F term, and now we have an overall distance for any given velocity. Now, this also assumes then that we have a way to calculate or know what that velocity is going to be at any given point. Now, what we'll see obviously is these forces are changing drastically throughout our entire ground roll. The distance along from our starting point, where we're starting off from zero velocity, then to our rotation of our aircraft. Now what you will notice, and we can look at this for both jet-powered aircraft and propeller-powered aircraft, realizing that our thrust variations are going to be slightly different for each of those. But in general, our lift is going to increase as we're increasing velocity. Likewise will our drag. However, our rolling friction is going to decrease. Since we're increasing lift, it will start off at a maximum value and decrease down to a lowest value of 0 once our lift is equal to the weight. And in general, the addition of those two is going to be approximately constant throughout the entire ground roll of the aircraft. So what we can do is then assume that our net forces are going to be relatively constant throughout this process as we look through the differences. Now this isn't an exact solution, it is an approximation, but it does give us very good results in assuming the values of these are going to essentially cancel out or equal out as we go through the ground roll, the portion of our takeoff phase. Now we do have to consider in our calculation for the lift the impact of ground effect. We talked about this briefly when we were looking at aerodynamic forces. Primarily what we need to know is the distance that the wings are above the ground. The closer the wings are to the ground, the greater impact that we're going to have in the ground effect. And this is going to impact not only our lift coefficient, but also our drag coefficient. So the ground effect has the impact of increasing our lift coefficient for a given angle of attack. So our wing is more efficient within this ground effect, but it also lowers our overall induced drag coefficient. So our aircraft is more efficient not only from producing lift, but also from producing drag, or a reduction in that overall drag coefficient. So we can look at the impact of our two curves, our lift curve and our drag curve, and notice that both of those are going to be improved within ground effect. And this, of course, has led to many cases over history where an aircraft is capable of flying, but only flying within ground effect if it just has enough power to be able to lift off, but not enough power to be able to accelerate and get out of ground effect. Now from this, we can go through the process of estimating the takeoff distance. And everything from here on out is going to be an estimation. We can take this equation and do it in numerical integration of it, and from that be able to do an exact calculation. We're not going to go through that process for our estimation of the requirements for this right now. What we're going to do is look at those forces that give us an average value to be able to estimate this overall takeoff distance. So benchmarking has shown that a velocity of around 70% of the liftoff velocity works pretty well in giving us an accurate number in being able to determine what that overall takeoff ground roller distance is going to be. So based upon our velocities we looked at earlier, we're going to take a liftoff velocity at 20% above the stall velocity. And since we already know the equation for the stall velocity, then we can then calculate the velocity at that liftoff point. We can take that, put that back into the equation, and then we're going to take an estimate of the thrust, the drag, the weight, and the lift at that 70% velocity of that liftoff velocity to give us an overall estimate. Now, if we want to be overly optimistic and then neglect the drag forces, we could actually take out those the drag and the rolling friction a piece of the equation to give us essentially a first stab of what this distance is actually going to look like. Now, there are some implications to this equation. So if we go back and look at this real quick, we'll see primarily the terms that we have in here that we want to focus on is going to be weight. Then we have things such as density. So our density altitude is going to be very important. Wing area, maximum lift coefficient, and thrust. So with this in mind, what we see is weight is extremely important. If weight of our aircraft is doubled, then takeoff distance is going to be quadrupled. So weight has the biggest impact on our overall takeoff requirement for our aircraft. Even small increases in takeoff are going to have a nonlinear impact on our overall, small increases in takeoff weight are going to have a nonlinear impact on our overall takeoff distance. So we have to be very cognizant of that fact when we're going through the design process. Also, as we note, density altitude is going to be very important. So we see density plays a role directly in the equation. So the density or takeoff roll or takeoff distance is going to be inversely proportional to density. But we also have thrust in there as well, and recall that thrust is also going to be impacted by density. So since thrust is typically going to be inversely proportional to our density altitude, then takeoff distance is going to be inversely proportional to density squared. So as we increase our altitude and go to higher and higher runways or higher and higher temperatures, then density is going to have a very, very big impact. So that's, again, one of the reasons why we typically look at summer, an August day, taking off from a high altitude airport such as Denver or Albuquerque as a good benchmark to make sure that our aircraft is going to be able to be capable of taking off in those conditions. Now, we also have things that we can use to help reduce our takeoff distance, primarily increasing CL max. and we'll use flaps to do that. And we can also increase our wing area, so we can use flaps to do that as well. And of course, we can also increase thrust as we go to a higher thrust. That's also going to decrease our overall takeoff distance. So once we have this equation, we can start to do some trade-off analysis. So with each of these to determine what's going to be the biggest impact. What we do note is if we drop weight, that's usually going to have the overall largest impact on our takeoff distance, since that is a square or nonlinear effect on our takeoff ground roll. Also notice, increases in CL max, they're going to have diminishing returns. So if you can go from a baseline of a lift coefficient of something like 1 to a value of 1.5, you increasing that by 50%, that's going to have a big impact. But in starting to increase that over and over those values, you do have diminishing returns since it's going to be asymptotic at that point. Now, it is worthwhile going back and reminding ourselves how much additional lift we're typically going to get out for any given airfoils. We can use benchmarks and generalizations to help us do that. Typically, most airfoils are going to have a stall lift coefficient of around 1.5 or so, and then once we put that on our wing based upon our sweep, we might reduce that for a highly swept wing down to around 1. So as we're adding additional flap configurations, moving from plain flaps, slotted flaps, Fowler flaps, then to multi-slotted flaps, all the way up to a triple slotted flap and slat, we might be able to easily double that lift coefficient, for these more advanced high lift configurations. Keeping in mind that if we go to greater high lift configurations, that's also going to increase the weight and complexity of our high lift design. So we can use these as general benchmark values to get us started. Now, what we're going to do is we're going to take these estimates then and put them into a takeoff spreadsheet to allow us to calculate the overall values of each one of these phases throughout the takeoff ground roll. So typically we're going to have a ground roll phase that's going to consist of wheels contacting the runway. Then we'll have a rotation phase as our aircraft starts to increase its angle of attack until we have wheels off the runway, so we no longer have weight on wheels acting on our aircraft. And then we're going to have a transition phase, which really you can think of this as a pull-out maneuver that we looked at in the previous lecture. So if we assume that we have a constant radius of curvature here, we then can calculate the load that's being imparted on the aircraft as we go throughout this phase until we transition into the constant climb phase for our aircraft. And we're going to calculate this entire distance, this total takeoff distance from the start, where our velocity is equal to 0, until we've climbed over this obstacle, which we're going to use typically 35 feet in our particular case. Now note that almost all aircraft rotate for takeoff, but not all aircraft. Some aircraft essentially have hiking nose gears that allow the wing to be at a larger angle of attack, and so you can think of this as a more gradual rate of climb. Many large vehicles, very large aircraft, things like the B-52 will typically have a very minimum rotation as they're going through the takeoff. Now, the rotation requirements really dictate the configuration of our landing gear. And this is something that we haven't talked a lot about within class, but you can start to see that this is going to have a pretty big impact. We have to think about the requirements from our forces being applied to the aircraft as it's rolling down the runway. So we want our aircraft to be stable, have the capability to rest on its wheels without tipping over while it's sitting on the runway or as it's rolling down the runway. But once we have significant dynamic pressure acting on our control surfaces, we want the pilot to be able to activate that rotation phase of the aircraft, essentially by providing a little bit of negative lift in a traditional configuration, or positive lift if you have a canard on the nose of the aircraft in order to be able to generate a moment to pivot about that center of gravity. Now, if we think about this from a force balance perspective, that coupling moment is going to be dependent upon the distance from your main gear, where most of your weight is acting at, and the location of the center of gravity. A common mistake in initial aircraft designs is to put that main landing gear too far back. If you put it too far back, it's going to require too large of a force to be able to impart that moment in order to allow your aircraft to rotate. So you really want to design that location of that landing gear with this in mind within a very short distance from that center of gravity, but enough to be stable. If you put too much junk in the trunk, then you're obviously going to tip back on the aft side of your aircraft. And that's one of the reasons that weight and balance management portion is not only critical during the flight phase, but also the loading and unloading phases of your aircraft. And of course, it is possible to have too much rotation as well. So notice the distance between the main landing gear and the aft section of your aircraft. If you rotate too quickly, then you can obviously hit your tail and do a lot of damage to your aircraft. Now, the next piece of this is the landing phase. So rather than going through this in detail, we're just going to take the same approach, except we're just reversing it. So we're going to assume that we have our aircraft with all wheels, touching on the runway, and then we're going to reverse the process. In this case, our touchdown velocity is going to be 30% above the stall velocity. You may think to yourself, well, why is that necessarily higher? Well, we're going to be lowering our stall velocity by deploying greater control surfaces. So typically our flaps are going to be deflected to greater angles for takeoff configurations. So that's going to provide us a lower stall velocity, but we want to have a little bit greater margin, so that gives us a larger cushion in case we need to abort our landing process or procedure. So this gives us more wiggle room, since as we're reducing the thrust on our aircraft and the ground is slowly starting to get closer and closer to our aircraft, or really the other way around, that we have a greater flexibility in being able to abort that takeoff. And we don't have something nasty happen to us like we saw with the A320. So in this case, we can apply the exact same equation. The only difference is going to be the behavior of our forces. First, we're going to have possibly a very small amount of thrust. As soon as our wheels are touching down on the runway, we're going to want to pull off on our thrust or apply thrust reversers to the aircraft. Our drag is going to be decreasing as we lower our velocity, and then our rolling friction is going to be increasing as we're dumping lift. And of course, our weight is going to be pretty much the same. We're going to use that same 70% point, which is 70% the velocity of touchdown. So we'll have a touchdown velocity as really that primary point that we're going to base everything around this particular calculation. Now, there are different requirements based upon what type of aircraft that you're using. So we're primarily going to use the FARs in this case, which determine that 30% velocity for your approach above the stall velocity. But if you're looking at other requirements, typically you'll have 20% above the stall for military aircraft. And then when you have a carrier aircraft, since you have tighter margins that you're working with, you'll typically be around 10% of that stall velocity. And again, that obstacle, that screen that you're going to be required to use as you're coming through the process is typically going to be around 50 feet or so. Now, you usually can use a rule of thumb that will give you an estimate of your total landing distance as 0.3 times your approach velocity squared in knots, as a way to essentially come up with an estimate for your overall requirement for your total landing distance. Keeping in mind that that's just a simple rule of thumb. Now for our overall landing process, we're going to have a descent phase, which is going to lead us then into the approach distance. So keeping in mind that we're not looking at typical airport traffic operations at this stage. We're just looking at the landing phase. So we'll have an appreciable distance where our aircraft is going to be on the glide slope as it's coming into the runway that we're not going to be including here in this calculation. We're looking at just the estimate of the landing distance. So this is going to start at that minimum obstacle height. So we're going to use that 50-foot value to start this calculation off at. We'll have an approach distance, which is going to continue that glide slope, which is typically going to be about -3 degrees. So as shown on this figure, this is obviously not to scale. That glide slope is going to be pretty shallow compared to what we're seeing on this graphic here. As we get closer to the runway, the ground, at a certain altitude, then we're going to have a flare, which is going to be, again, that pull-up maneuver. And we can assume that we're going to have a constant radius of curvature as we go through this pull-up maneuver. And as we flare the aircraft, we're going to have wheels touch down on the runway. Our nose is going to pitch down. And once we have full contact with our landing gear with the runway, we'll transition from a free roll portion to a braking portion where we apply brakes and or our thrust reversers acting on the aircraft, and that'll give us a total then ground roll calculation for our distance. Now this piece here is obviously pretty critical. The landing distance phase, that's typically going to be the most dangerous portion of your aircraft flight. So here's an example. This is a NASA hard landing test. This puts in mind the requirements that we're going to see on that VN diagram in terms of designing for various impact forces acting on our aircraft. A hard touchdown can obviously have very detrimental consequences for the structure of your aircraft. So this is something that you want to take in consideration as you're going through this overall design process. Now, as I mentioned, there is a lot going on in the descent. Just so that you're aware with what's happening, for most aircraft, as you're coming into the pattern, this is going to be dictated either by looking at your directory that's going to tell you, whether you're going to be coming into a right-hand or a left-hand pattern, or whether you're going to be guided in by air traffic control. You'll have a certain sequence that you'll start into for your landing phase for your aircraft, where given a certain glide slope, you'll be able to then determine what that distance required needs to be to get you from that entrance into your glide slope then into touchdown for your aircraft. This will often be dictated by other traffic in the area, making sure that you have safe separation between your aircraft and the aircraft that you're following. And then, of course, the aircraft that's following you as well. Now, there are different ways to do this. You can have a continuous descent approach, meaning you have a constant glide slope, whether you're doing this under visual meteorological conditions or whether you're using an instrument landing system in order to provide your glide slope requirement as you're coming in for touchdown of your aircraft, or you may be going through some other type of step-down approach. In this case, this might be dictated by other factors based upon the local conditions or runway requirements that you have for your aircraft, particularly in urban areas where they're typically more concerned about the impact of noise from a descent, so that way you don't have your pilots running your engines up and down to create more noise, but also to reduce your overall fuel burn and the impact of pollution on those urban environments. Now, once you do touch down, in addition to braking on your aircraft, you may also have the possibility of deploying thrust reversers. And typically you have two different types of thrust reversers. One is a cascade thrust reversers that you'll see most often on high bypass ratio engines, where part of the cowling on the nacelle slides back, opening up in a region for your flow, typically through the cold path of the fan section of your engine, to be deflected forward at an angle. And this does two things. First, it dumps that thrust, because you can't just turn the engine directly off. It's still spinning. It requires some time to spool down. So there is going to be a delay in the impact of how long it takes for the pilot to input control to the thrust of the engine, with how long it takes for that thrust then to change on the engine itself. So this gives you the capability then to essentially stop producing thrust in the direction that you're flying. So you're able to dump that and then put a little bit of that, at least, pushed in the direction of flight. And here's an example of typical cascade thrust reversers. You'll either have doors that open up, or you'll have a piece that will slide back on your engine. You'll notice the flaps here are also deployed in a landing configuration. An older type are going to be clamshell thrust reversers. You'll see that on our MD-80, for example, which is a derivative of the DC-9. So you'll see these on both medium and low bypass ratio turbofans. Now these have the advantage of deflecting all of the thrust, so not only the cold portion or the bypass around your turbofan, but also the flow going through the hot path of your engine. And you'll notice that the thrust is not being completely pushed back into the direction of flight. You only have a component of that, but that does have a significant impact on the decrease in your landing ground roll. And here's an example of a cascade design combined with a clamshell system that's used on a C-17. In this case, military requirements often have the need of reducing the amount of ground roll as quickly as possible. Now, there are additional ways that you can slow down. In some cases, you can use things that will help essentially break the amount of aerodynamic forces that you have out in an aircraft, not only to spoil the lift, but also to create air brakes. Things such as split ailerons. You can use things such as parachutes or even cables, which you'll typically see not only on carriers, but also in some land runways as well for very short ground roll maneuvers. Now, the last piece we're going to talk about is what's called the balanced field length. And when we run these calculations for both takeoff and landing overall distances, those are going to be much lower than we're going to have in terms of the requirement that we're going to need to satisfy the FARs. Typical runway length is going to be 50% to 2 times over the takeoff distance, because it requires us to be able to include the impact of that OEI scenario. Let's say we're rolling down the runway, we're taking off, we have a twin engine aircraft, all of a sudden we lose an engine. We have to make the decision of whether we're going to brake the aircraft, so we have to include the stopping distance at that point, or whether we're going to continue with that takeoff requirement and then go around to be able to have an emergency landing. So this dictates a couple things about our aircraft design. First off, our aircraft still has to be able to take off if we lose one engine. And so if we have a modern twin engine airliner, something like a 737, we lose an engine, we still have to be able to take off with one engine. So not only do we have to design that aircraft with the power sufficient to be able to continue takeoff with that one engine, so each of those engines by themselves provide the capability to take off, but we also have to be able to control that aircraft with the asymmetric thrust acting on it with that OEI scenario. Now, our alternative is if we're below that decision speed and we lose an engine, then we want to be able to decelerate. So we essentially have to run through a calculation of takeoff from zero velocity to that decision speed, and then run a calculation of our braking or our landing distance from that decision speed all the way back down to zero velocity. And that's going to determine our minimum runway length requirement. And that's where the name balanced field length comes from. It's a balance of both your takeoff and your landing distances. So here's an example of how we go through that process for that balanced field length takeoff requirement. As we're going through the process of running down the runway, our velocity increasing for a given point on that runway, when we reach that critical decision point where we lose that engine, then we have to ensure that we have the capability, if we're right at that point, of either accelerating and continuing our takeoff ground roll to be able to take off with an OEI scenario, or decelerating till we get to a stopping velocity equal to zero. So we can typically think of this balanced field length portion or this critical failure point as the worst case scenario. If we happen to have an engine fail at that critical failure point, that's going to be our maximum possible runway length that our aircraft would utilize. Now, as part of this calculation, we do have to know what value of rolling friction we're going to utilize. Nominally, we're going to be operating the aircraft on dry concrete, but there may be cases where we'll have other scenarios as well. Obviously, if our concrete is going to be wet, our rolling friction is going to be different. It's actually going to be slightly increased during the takeoff phase, but when we apply brakes, it's going to be decreased. So we have to ensure that our aircraft is going to be able to land on a wet runway as well. If we happen to be landing in icing conditions, obviously, that's going to lower the rolling friction too. Now, there are cases, we might have aircraft that are designed to land on austere runways. So we have to do calculations for things such as hard turf, dirt, or grass. And of course, in many scenarios, you'll have specific design configurations for your aircraft in mind, typically when you're looking at bush aircraft designs. So this finally gives us the information that we need to go through the process of running through calculations. So at this point, you'll be able to use the takeoff and landing spreadsheet, putting in the parameters for your aircraft and runway configuration to be able to run through calculations and estimates of those different phases for both takeoff and landing. So that spreadsheet will provide you the capabilities to look at each one of these phases for the ground roll, rotation, transition, and climb for takeoff, approach, transition, free roll, and then braking for your landing phases. Keep in mind that these, again, are estimates based upon those equations that we derived at the 70% velocity point. So we already talked a little bit about short takeoff and landing and ways that you can decrease both those takeoff and landing distances. There are essentially two approaches. One of those is to increase your lift, primarily through high lift devices, and the other is to increase your thrust. So that way, either applying extra thrust in the direction of flight or powered lift, so that way you have thrust acting directly against the weight of your aircraft. Good example of that is our V-22. Notice our V-22 is going to be designed to take off vertically, but then it can start to transition pretty quickly. So you could apply a similar concept to this to be able to essentially tilt those rotors over so that way you can roll down the runway. And once you know what that angle then is, you can apply that directly to your equations with the thrust being applied in the direction of light being multiplied by cosine times that thrust angle, and then the impact of that thrust acting against the weight of your aircraft in order to reduce that overall rolling friction acting on your vehicle. You can also, of course, apply additional systems on your aircraft, such as rocket-assisted takeoff, with the most important thing being in mind when you start to do something like this, make sure that that thrust line is acting through the center of gravity of your aircraft, or if it isn't, that you're able to overcome that moment with no dynamic pressure acting on your control surfaces, because you will be starting off at zero velocity. Now, the final piece for pilots, what you'll typically see is a takeoff chart that will come with your aircraft manual that will give you indications of what your required takeoff and landing rolls are going to be, your ground roll, your total distance over that 50-foot obstacle, your takeoff speed, and then allow you to apply corrections for things such as density altitude, increase in weight of your aircraft, as well as looking at both headwinds and tailwinds, and even changes in that obstacle height. So then you can use these charts to determine what that overall runway distance needs to be, which you can look up on airport directories prior to operating from that particular runway under any given set of conditions.